This video explains the astronomy of the ancient Greeks. There were many overlapping timelines, so that which happened, as we saw before, in ancient India, even ancient China, was happening contemporaneously with events in Greece, Egypt, and Rome. So ancient Greece was started around 6000 BC when we had farming, and 2000 BC we had the first Greek civilization, the Cretes. And it continued on until about 323 BC, the time of Alexander the Great. And at that point, Rome has pretty much taken over. Rome and Greece, though, grew very contemporaneously. Rome was founded in 753 BC by Romulus, and we see the fall of the Roman Empire in AD 476, although the Eastern Empire survived until 1453. Then we have ancient Egypt going back to 6000 BC, which we've already covered some of the astronomy of the pharaohs. The learning goals of this lecture are that we're going to touch on the advancements of timekeeping and star cataloging that the Greeks made, but the central focus is really on the cosmological views and the explanation of planetary motion. So the learning goals are to understand that ancient Greek astronomers reasoned that the universe was geocentric, and that the Aristotelian cosmology, which dominated Western thinking until the Copernican revolution, regarded the laws of physics on Earth as unique and separate from those in the heavens. Ptolemy developed a system for explaining the motion of planets that was consistent with the observations for centuries, and provided sufficient ad hoc modifications continued to be made. This picture is of the Tower of the Winds, an octagonal marble clock tower in Athens. The structure features a combination of sundials, a water clock, a wind vane, and was supposedly made by Andronicus of Cyrrhus around 50 BC. And according to other sources, it could have been the 2nd century BC. In the early Christian times, it was used as a bell tower by the Byzantine Church, and later the Ottoman Empire, though it was still half buried, the Islamic Sufis used it for performing whirling dervish ceremonies. In the geocentric view, the Earth does not move. It is considered fixed or stationary at the center of the universe, and the sun, moon, and planets and stars all rotate around Earth. Thales was a philosopher who traveled extensively and brought astronomical records from Mesopotamia and Egypt to Greece. He believed that the Earth was a disk floating on an endless ocean. By some accounts, he correctly predicted a solar eclipse in 585 BC. Anaximander was a philosopher who made detailed maps of the Earth and sky. He believed the Earth was spherical and unsupported and free-floating. He is thought to have brought sundials back from Mesopotamia and Egypt to Greece. He conceptualized space as having depth. He measured the circumference of the Earth, and he modeled celestial bodies making full circles in their orbits, which led to the Pythagorean paradigm, which we'll talk about soon. So let's talk about the nature of science. In the 7th century BC, a common viewpoint was that the universe was a rational place, following universal natural laws, and we were able to figure those out. They believed in open inquiry, and critical evaluation was highly valued. The emphasis was on process of learning about the universe rather than attaining the goal. But of course, people got tired. They wanted answers. Science doesn't always give us absolute certain answers. In fact, it doesn't ever give us absolute certain answers. And there was disagreement among the experts, and there came to be a crisis in confidence that led to the rise of the sophists. These sophists taught that an absolute truth and morality are myths and are all relative to the individual. Socrates disagreed with the sophists. He taught that we can attain real truth through collaboration with others. By exploring together and being skeptical about common sense notions about the way things are, we can get a correct understanding of how our world and society operate. Please note that a lot of the lecture notes from this lecture are coming to us from Nick Strobel's astronomy notes. So science has the problem of induction. No matter how much evidence we have for a conclusion, the conclusion could still conceivably be false. No matter how much evidence we have to continue to test it and test it and test it. the more positive cases that favor a hypothesis, the stronger it is. And you recall that a hypothesis can eventually become a theory, and then a theory, if it's very important, can become a law, provided that it's subject to much testing and passes all those tests. The most logically sound samples are those that represent an entire set. It is possible to make true conclusions from false assumptions, certainly, but a hypothesis can only be confirmed. It cannot be proven to be absolutely true. Even though scientific hypothesis cannot be proven to be absolutely true, that does not mean that it's false. So all that's logic and reasoning, and we can see that the origins of this kind of logical reasoning do go back to the ancient Greeks. The origin of the cosmological principle is Socrates taught us to be skeptical of common sense notions. The common sense notion or paradigm of the day regarding astronomy originated with Pythagoras. Pythagoras said that there were three key points about the movements of celestial objects. The planet, the sun, the moon, and the stars move in perfectly circular orbits. The speed of the planet, sun, moon, and stars in their circular orbits is perfectly uniform, and which means it's always constant, it's always the same. And the Earth is at the exact center of this motion of the celestial bodies. Plato attempted to explain retrograde motion of the planets. Retrograde motion is the motion of a body, either real or apparent, in a direction opposite to that of its normal motion, or that of other similar or related bodies. Since a body in motion stays in motion, that's inertia, we have to explain retrograde motion in terms of forces. Apparent retrograde motion is explained in terms of frame of reference. The retrograde motion of Mars and Uranus in 2003 are shown here. This composite image created by superimposing images daily taken on 29 different dates. Here's the retrograde motion of Mars in 2005. A composite image is created by superposing images taken on 35 different dates. And here's the retrograde motion of Mars in 2012. Observations that convinced the Greeks the Earth was not moving included that it was not part of the heavens, that the celestial objects are bright points of light while the Earth is an immense non-luminous sphere of mud or rock, that the Greeks saw little change in the heavens. The stars are the same night after night. In contrast, they saw many things changing on Earth. It was the home of birth and change and destruction. So they believed that the celestial bodies have an immutable regularity that is never achieved on the corruptible Earth. Finally, our senses show that the Earth appears to be stationary. We don't sense its motion. Air, clouds, birds, and other things unattached to the ground are not left behind as they would be if the Earth was moving. So there should be a strong wind if the Earth were spinning, as suggested by some radicals, and there is no strong wind. So they didn't have that concept that we have today of inertia. Also, they were not able to measure stellar parallax. Stellar parallax is the apparent change in position, relative position, of something near to us compared to something far. Plato and his students worked to provide a geometric explanation for the apparent motion of the planets, especially the strange retrograde motion. In this time frame, Aristarchus developed a model of the sun with the sun at the center of the solar system, but it was rejected because of the obvious observations against a moving Earth. However, some people feel that Copernicus resurrected Aristarchus's work later in the Copernican revolution. Plato taught that since an infinite number of theories can be constructed to account for the observations, we can never empirically answer what the universe is really like. He said that we should adopt an instrumentalist view. Scientific theories are just tools or calculation devices and are not to be interpreted as real. Any generalizations we may make may be shown to be false in the future, and also some of our false generalizations can actually work. An incorrect theory can explain observations and could be practical. So Plato took that instrumentalist point of view. Aristotle proved the earth was spherical, as you recall. He modeled the geocentric universe of the sun, planets and stars as being located in spheres that revolved around the earth. He was a student of Plato. However, after Plato's death, he shifted from instrumentalism to empiricism. He was also a teacher of Alexander the Great. So sciences, all of them, anatomy, astronomy, embryology, geology, geography, meteorology, physics and zoology, ethics, aesthetics, metaphysics. He wrote about all these things. He was an immensely intelligent person who kind of wrote down almost everything that the Greeks knew. Aristotle, who was the student of Plato, is regarded to have the most influence in history on modern scientific theory. He taught a realist view. Scientific, mathematical tools are not merely tools, they characterize the way the universe really is. And at most, one model is correct. He also had a cosmological model. This model of Aristotle chose was one developed by a former follower of Plato, Eudoxus. The planets and stars were on concentric crystalline spheres centered on the Earth. Each planet, the sun, and the moon were on their own sphere. The stars were placed on the largest sphere, surrounding all the rest. Aristotle chose this model because the most popular, and there was observational evidence that supported it, and his physics and theory of motion necessitated a geocentric, Earth-centered universe. Also, the crystalline spheres model agreed with the Pythagorean paradigm of uniform circular motion. Aristotle's cosmology had 55 crystalline spheres. These were spheres that were concentric around the Earth and moved in uniform circular motion. The sphere stars lay beyond the ones shown here for the planets. And finally, in the Aristotelian conception, there was an outermost sphere, and that was the domain of the prime mover. The prime mover caused the outermost sphere to rotate at a constant angular velocity, and this motion was imparted from sphere to sphere, thus causing the whole thing to rotate. Aristotle had a realist view. In Aristotle's theory of motion, things naturally move to the center of the Earth, and the only way to deviate from that is to have a force applied to the object. For example, if a ball were thrown parallel to the ground, it must have a force continually pushing it along. The Greeks had no concept of inertia, and this idea was unchallenged for almost 2,000 years until Galileo showed experimentally that things will not move or change their motion unless a force is applied. Aristotle abandoned the cosmological principle. He thought that the Earth was unique with its own set of physical laws, and these were different from how things worked in the heavens. The Earth was a world filled with change and decay, while the planets, the moon, and the sun were perfect, unchanging, and essentially ornaments in the sky, not worlds that could be explored. As we mentioned before, Aristarchus proposed a heliocentric model of the universe, and he attempted to measure the distance between the Earth and the sun and the distance between the Earth and the moon. His argument for doing this was very sound. His mathematical reasoning was very good, but his measurement was imprecise, and his views were not widely accepted. The Greeks advanced timekeeping. In 250 BC, Apollonius of Perga used conic sections upon which the hour lines were inscribed to provide greater accuracy in their sundials. This particular picture is a Roman sundial, but it was very similar to the hemicycles created by the Greeks. Ptolemy was a Greco-Roman writer of Alexandria. He was a mathematician, astronomer, geographer, astrologer, and poet. He espoused a geocentric model that predicted the sun, moon, and planets, and he was able to explain the retrograde motion. So he assumed that objects moved at a constant speeds in their circular orbits. It's one of the longest upheld scientific theories in history. It was based on observations recorded by Hipparchus and from Babylonia a long time ago. The Almagest, he wrote, was the first astronomical treatise, has an Islamic name because it was translated from Greek to Arabic. The Ptolemaic system is a description of the cosmos where the Earth is at the center of all celestial bodies. The universe consisted of a set of nested spheres in which he used the epicycles to predict the positions of objects. Ptolemy estimated that the sun was at an average distance of 1,210 Earth radii, whereas it's actually 23,250, while the radius of the sphere of the fixed stars was 20,000 times the radius of the Earth. Ptolemy's system used epicycles and difference. The planets moved on small circular paths called epicycles, and the center of these epicycles moved around Earth and other circular paths called difference. The combination of planetary motions along epicycles and deference produces observed wandering of the planets. So he was able to explain the retrograde motion with this system. And here's showing the paths of the epicycle and then around the epicycle, and then eventually the deferent motion was offsetting the Earth a little bit from the center. So they had to continually make slight adjustments to this model to make predictions. Ptolemy's estimates of orbital sizes are not too good compared to modern views, but at least they all kind of go in the same predictive fashion, that he's got them in the right basic ordering, just orders of magnitude off. You needed lots of epicycles to accurately track the planetary motions, especially retrograde motions, with Ptolemy's model. This animation shows how the system worked to explain retrograde motion. Ptolemy promoted an instrumentalist point of view. It was a complex model of epicycles. It was incompatible with Aristotle's model and Pythagorean paradigm. So a planet on an epicycle would crash into a crystalline sphere, and the motion was not truly centered on the Earth. Ptolemy had to adopt this instrumentalist point of view so that he could maintain belief in the Aristotelian realism. So this strange model, he thought, was only an accurate calculator to predict the motion of planets. But in reality, Aristotle's model is what's really going on in the universe. So he explained this apparent contradiction between reality and a calculation device as just being, well, this is as good as we can do today with our instruments and our knowledge. Our modern belief that models must characterize the way the universe actually is a tribute to the ever longer lasting influence of Aristotle's realism. Ptolemy also improved timekeeping. He added an analemma, and he found through geometrical constructions on a plane those arcs and angles by which specific points may be determined on the celestial sphere. Eratosthenes measured the distance between the Earth and the Sun and the axial tilt of the Earth. He is considered the father of geography, and he mapped the world. Hipparchus was the greatest astronomer of ancient times. He made the first known star catalog. He invented the magnitude scale. He measured the distance to the moon to be about 29.5 Earth radii and discovered the precession of Earth's spin axis. The Farnese Atlas is a 2nd century copy of the Hellenistic era statue depicting the Titan Atlas holding the celestial sphere on his shoulders. It is the oldest surviving depiction of an ancient Greek constellation map, and it includes grid circles that provide coordinate positions. The Romans also made advancements in timekeeping. In 164 BC, the first sundial was constructed for the city of Rome, designed by architect and engineer Marcus Vitruvius Pollio. Greek sundials evolved from earlier Babylonian inventions, and Pollio mentions many different types of sundials in his great work De Architectura. Later Greek advancements in timekeeping include they discovered that if you had the gnomon slanted and parallel with Earth's spin axis, it would be much more accurate throughout the year. And they also developed trigonometry in 150 AD, and the Islamics furthered that development of trigonometry. It was used for plotting the hours of sundials, and it was the basis of sundial construction used by Arabs and later by Europeans. So in summary, we had better timekeeping throughout these years with sundials, and we had cosmological developments. Aristotle's philosophy prevailed regarding how the universe was organized, but Ptolemy's model was used practically to predict the motions of celestial bodies, and it was sufficiently accurate for many years to come, but it required many ad hoc modifications.